Welcome to Starborn Science. This is my best ZVS Tesla coil. Power supply, pulse generator, ZVS driver, Tesla coil. That's my mom's. That's an artificial ground. Let's fire it up. I like it. Ooh, I had it in my pocket. Isn't great, right? The humble ZVS driver. Ooh, it smells like ozone. It's not yet hot. Let's run for a bit more, shall we? It's a goddamn beast, isn't it? Look at this arc. It has to be about 10 centimeters. It's absolutely fantastic. Took me ages to want that coil. That's actually running on 50 volts right now, and I'm pushing it. I'm really pushing it. But let's get into some theory. So now that we've seen how a ZVS driver works, well, this is also ZVS driver, right? ZVS drivers can be used to run many things, like an induction heater. That's why I had this coil screwed on as a load. Let me get my flyback. So we can screw on a flyback transformer, get some arcs from a high voltage transformer, and those are all very valid and classic uses for ZVS drivers. And let me power this thing up. Yeah, as you can see, there's an arc that's sticking between the two electrodes. So that's one way that you can get high voltage out of a ZVS driver. But what if I told you that we can run a Tesla coil out of a ZVS driver? But first, how to control a ZVS drive? Well, you'll say, that's a dumb question, right? Well, let's see. power up a ZVS driver and probe it. There goes screwdriver. And you'll see a continuous wave, meaning no matter how much I zoom out, it's a continuous wave, a sinusoidal wave. In this case, the driver is self-resonant. It's a two-inductor driver, that version of the ZVS driver. It self-oscillates at 93 kilohertz. And yeah, so now that's one way, right? Now let's take a different approach, but first let's get to the arrogance part. So this is a self-resonant system, and most of all, it's a resonant system, right? So what is also a resonant system is a Tesla coil. It's primary coil and the secondary coil that, when tuned together, form a resonant system. Yeah, but when I first thought of combining a ZVS driver with Tesla coil, I was kind of down, and I was expecting to just connect a ZVS driver to a Tesla coil, like that, and expect to have arcs and sparks. Well, you guess how that went, right? Yeah, well, let me fetch a different driver, because this one has two MOSFETs that are not up to the task for this load. So my expectation was to just connect a Tesla coil to a ZVS driver, and since both systems in my mind were resonant systems, I was expecting to get instant gratification. Well, that's not how it goes. So was this thing capable of lighting up anything? No. Maybe. Let's see. What? Maybe an LED? Yeah. It would light up an LED. Maybe a neon bulb? It would light a neon bulb. If you stuck it close to that. If you got the ground to the breakout point up top, you would even get a spark. Wow, right? Well, that's not a Tesla coil though, is it? So, what did I get wrong? What was wrong in this system? Well, let's take a measurement and see. So this system, according to my scope, is self-resonating at 420 blaze it kilohertz. Nice, very nice. So yeah, judging from this size of the coil, that's not even close to the resonance frequency of the secondary. So what was going wrong was very simple. And I felt really dumb when I realized what was going wrong. And what was going wrong was that the ZVS primary coil system, this and this, when powered together, locks on a certain frequency, in this case 420 kilohertz. If that frequency is not the same as the natural resonance frequency of the secondary coil, then there's no maximum energy transfer between the two systems. Hence, there are no arcs, no nothing. So that was my problem, right there. So now let's go to the next part. Controlling. So now let's go to the next part. Controlling the ZVS driver. As I said in the first part, controlling it is just, well, powering it, and went up with a continuous wave, right? Just like this. If I get my camera to focus. It's apparently not easy, but yeah, you get the point, right? So that's one way of controlling the ZVS driver. Another way is pulsing it. And to pulse it, we are going to use a pulse generator, which is this beautiful device. What we have here is a MOSFET switch, the pulse generator, this board, a gate resistor for the MOSFET, a Zener diode in order not to fry the MOSFET, and the pull down resistor from gate to source in order not to fry the Zener diode. This powers the generator. This is the power input to the MOSFET, and this is the power output to the ZVS driver. And end up with this contraption over here. Now you will wonder why I added this inductor over here. It will make sense, I promise. So let's power up the generator. Oopsie. we'll power it up with 12 volts, and we will set it at 500 Hertz, meaning it turns on and off 500 times per second, and at 50% duty cycle, meaning the transistor is 50% on and 50% off per cycle, and that's how we control the power input by adjusting the duty cycle, and that's called pulse width modulation, or PWM, because we actually control the width of the pulses, and that will make sense on the scope. So let's power the ZVS driver. Through the generator. Now, one channel will be showing the square pulses given by the MOSFET, by the generator to the MOSFET, and the other channel, which is why I added this inductor, will be showing the response of the ZVS driver. Now, the reason I added this inductor is because my scope has a common ground, and if I probed the ZVS driver and the pulse generator, it would short inside my scope and short the ZVS driver, and it would short out. So I'm gonna probe it by inductive coupling, essentially. And now let's see if my camera focuses. Come on, camera. Camera doesn't wanna focus. So what we're seeing here is each square pulse is followed by a resonant ringing of the ZVS oscillator. If I zoom in, oopsie, we will see that each pulse is followed by a resonant ringing. Of course, here in the beginning we have a spike that then gets smoothed out as the ZVS takes on, and throughout the length of the poles, the ZVS is completely on, and as soon as the pulse drops to 0 volts, we have some artifact over there. The ZVS turns off, there's a ringing that before it drops to 0, and then it drops to 0, and then the cycle continues, and on and on. So that's how we actually power the ZVS driver, not in continuous wave, but in pulse mode. Why? Because it's a lot more energy efficient. The MOSFETs don't heat up as much. We can run it at much higher voltages than we could if we run it at a continuous wave cycle. We can run it up to 50 or 60 volts even, which would be a really dangerous territory if we used continuous wave. Personally, I run my ZVS drivers at about 40 volts to keep it safe, because I've tried drivers and those MOSFETs cost about 5 to 6 euros a piece, so it's not cool to fry them, because when they get fried, they usually get both fried, not one of them gets fried. When there's a catastrophic failure, usually both of them get blasted. So yeah, that's usually 12 euros gone to waste, and lots of work of soldering and stuff. So yeah, be reasonable with your voltages. And of course, I'm gonna show you I'll decrease the duty cycle, and you'll see now it's to 0. Now I'm increasing it now to 84, and you get how we control the power input by increasing or decreasing the duty cycle in the system. Now it's set back to 50%, and that's about how we go on controlling it. And of course we can change the frequency, and that's another way we can control the power. But controlling the duty cycle and having a set frequency is the most efficient way to do that. So that's about all on how to control it. So now let's get to the fun part. Let's see actually how one of that sweet babies run, right? That's why you're here for. So what do we have here? Like, we have our power source, right? Now we have a boost converter that's set to 40 volts. We have an RF relay that's triggered remotely. We have two 18650 batteries with a small boost converter that powers both the RF relay and our pulse generator. We have the boost converter getting the power in the pulse generator. This power MOSFET switches the power according to the settings in the pulse generator in the ZVS driver. And we have our primary Tesla coil, our primary coil of the Tesla coil, tuned with the ZVS driver to the frequency or to the resonant frequency of the secondary coil of this Tesla coil primary secondary system. So this time we should expect arcs. I also have to add that because I'm in an apartment, I do not have a stick to hammer into the ground as a ground, and of course I cannot use my mains ground as a ground because it has to be a low inductance path, so that can be used. So don't do that. Please don't do that. You're gonna fry your electronics and don't do that. Don't connect your Tesla coil ground into your mains ground. So also some specs on this driver. This driver has two toroids. Each one is rated for 17 microhenry. These are two Schottky diodes rated for 10 amps and 650 volts. These MOSFETs are two IRFP 260N MOSFETs, and this capacitor is a polypropylene capacitor rated for 150 nanofarads and 1000 volts, and the primary coil is 2 loops of 16 gauge or a WG something. I don't know what kind of measurement that is, but yeah, in diameter or something. And the secondary coil is painstakingly made by me, yours truly, and it's 1500 loops of 0.1 millimeters of double enameled copper wire, and we have a breakout point over here. So let's see. Our pulse generator is set at 400 Hz and 65% duty cycle. I'm gonna take my camera back because of electromagnetic interference. And I'm gonna fire this baby up. Also, yeah, this is an artificial ground. I don't remember if I mentioned that. Anyway, so let's fire it. Get the lights off. So it looks a bit more dramatic. Just a coil a bit. Maybe. Let me change the batteries. So changing the batteries was clearly a good move. You can see the corona discharge now is a lot better than before. Let me retune my primary, maybe I get bigger arcs now. Who knows? Yeah. Of course, goes without saying that we can light light bulbs. So the sound you're hearing is not the Tesla coil itself, it's the 100 Hz sound. We have set the Tesla coil pulse frequency. It's like a DT RSSTC that actually punches air with radio frequencies in essence. So yeah, that's what we're hearing in essence. It's not the arc is actually producing sound because of the pulse frequency we have set our pulse generator at. If I set the pulse generator to 500 Hz, we will hear sound corresponding to 500 Hz and so on. If I set it to 1 kHz, you will hear a 5 kHz sound. I'm not doing that because then I'll have to readjust my primary coil, because it's time you mess with the pulse frequency, the resonance frequency of the system changes a little bit. So enjoy it as is. So I'm gonna demonstrate it a bit more. Let's see if we can get bigger arcs by getting the primary, I don't know, a bit more down, maybe. No, the resonance point is higher up, it seems. about there, probably. Oops, my camera. My camera got. Yeah. There you go. I'm gonna be risky and get a bit closer. And yeah, I'm not gonna run it for much longer because those batteries are getting hot. This thing is drawing probably 5 to 6 amperes and it's set to 40 volts, so the system is drawing about 200 watts, so yeah, that's not good. In general, batteries, lithium-ion batteries and heat do not go well together, so yeah. And now I'm gonna show you a more polished version of a system that actually has dials on it and meters and switches, and you'll see how much power it actually draws. So let's go there. So now this is my most polished version. As you can see, it has a nasty baking tray as an artificial ground, which I'm gonna bring closer to it to increase the arc length. It also does not have a classic ground breakout point. It has a loop antenna as a ground point, a single loop antenna, and it has also an amp meter and a voltmeter. So let's fire this baby up. And as you can see, it's drawing 40 volts and 5 amps. So yeah, it's drawing lots of power, and this is not something you wanna mess with. It's not the kind of Tesla coil you wanna touch with your hands. These arcs may look cool, but because the ZVS driver can push a lot of power through it, these arcs can carbonize your skin instantly. RF burns are not to be, you know, messed with. They can cause serious damage. I'm not joking around. You can really cause serious damage to yourself. Don't do this if you don't know what you're doing. You can. It's not that you're gonna get electrocuted by that. The frequency of operation is so high that the nerve cells do not get depolarized, so you're not gonna get electrocuted, but you're gonna get flash burn by it. I'm telling you this because it happened to me and it burns like hell. So don't do that. So yeah, that's about it. I hope you enjoyed this episode of Starborn Science, and on to the next one. Till then, keep dreaming, keep exploring, and I'll see you on the next one.